Hello everyone, my name is Mohammad Sajid Akhtar and today I am going to present a small presentation on the design of novel H infinity robust control of a hydropower plant to suppress the ultra low frequency oscillation. Okay, let us start. These are my outlines of this presentation. I will start from the introduction of the robust control, then what are the design process involved in this robust control, then a case study, that is the main topic, that is the designing a H infinity control for a hydropower plant, then comparison and result analysis, and finally the conclusion. Okay, let's come on the introduction part. We know that when we design a control system, our ultimate goal is to control a particular system in a real-time environment. For this, there are various control are available like simple closed loop control, PID control, classic control, and also robust control. And every control has their own advantages and disadvantages. But the ultimate goal of all the controls is to ensure the high performance of the plant. But a robust control has a unique feature that it ensures the performance even after meeting various uncertainties and changes in the parameters also. So come across the definition of the robust control, that we can say that robust control is a systematic approach for designing a controllers which can withstand even after various uncertainties and maintain stability and performance level despite of various conditions and even the changes in the parameters. Here is a figure, that is, you can see that is a block diagram of the robust control, and you can see that the uncertainty come across the plant in three places. It may come through by the three places. There are some uncertainty in the model also, that is in itself in the plant. There may be some disturbance from the outside world which also introduce some uncertainty in the closed loop system, and there may be some noise in the signal that is going to be read from the plant sensor. So we have to counter all these uncertainties through the designing of the robust control. These uncertainties may be either in the additive in nature or maybe a multiplicative in nature. So we can say that the robust control is the best way to handle the uncertainty of the plant. We already know that the PID control is one of the best method, and they are successfully implemented in the various industrial application. So this robust control is a new feature which excels over PID, and they are now introducing in the various real world conditions. Unlike PID, which relies only on some fixed parameters, robust control adapt ensuring performance in changing environment also. There are various type of robust control, and we can discuss three of them. The main of them are the H infinity control, mu synthesis, and the adaptive control. So what is H infinity control? Actually, this type of control utilize H infinity norms to design controllers ensuring robust performance despite uncertainties, as already I defined. The H infinity norms, this is a new term. Actually, what is that? This is a mathematical measures of the largest possible gain that a system can have from a given input to the given output. That is the main fundamental of the H infinity control. We can see in further slides. Second one is the mu synthesis. Actually, mu synthesis is an extension of the H-finity control where the plant output is uncertain and tries to minimize the worst case gain given is the uncertainty condition. So it emphasizes on the worst case gain. Third is the adaptive control. Actually, the adaptive control is more focused on the real-time parameter adjustment to deal with the changing system dynamics. While H-infinity control is focusing on designing controllers that offer optimal performance and robustness against uncertainties. So these are the major difference between all three types of robust control. There is a mathematical expression. You can see this is the H-infinity control, and it normally used to minimize the H norms of the transfer fixed function and given by this mathematical expression. So the nutshell, the controller is to design to minimize the worst case effect of the disturbance or output or error signal. So the two basic objectives of the H-infinity controls are to minimize the maximum error energy of all command or disturbance inputs with bounded energy and closed loop stability under unstructured plant uncertainties with bounded H-infinity norms. These are the two basic objectives of this H-infinity control. And we have to take care of these two objectives while the designing of this H-infinity controller. Here there is a basic block diagram of the H-infinity control where G is the plant. You can say this can be the transfer function of a plant, and the block is the for a plant. K is the controller, and this delta is the uncertainties or external disturbance. Here you can see there is two inputs. W is the inputs including reference signal and disturbance. There are two inputs there are in the plant. One is the W and second one is U, where W is the reference signal as well as the noise or disturbance which is going to be fed in the plant. U is the control input which is given by the controller. Z and Uy are the outputs of this plant, where Z is the error signal that need to be minimized in order to fulfill the objectives of the controller, and Y is the measured output. These are the basic block diagram. Now we are discussing what are the different procedures to designing a H-infinity control. First of all, we have to obtain a plant transfer function and get system matrices through the MATLAB. There are various commands for that. Then we have to define or find two weight functions. Actually, these weight functions are very important while designing a H-infinity control. There are majorly two types of weight function, that is WS and WT, which is called the sensitivity weight function and the task weight function. So there are some procedure through the MATLAB. We can just define this weight function. Then we have to go to create an augmented plant by a command augtf from the MATLAB control toolbox. Then we have to perform a H-infinity synthesis through the command hinf, which minimize the sensitivity of the system to ascertain while meeting defined performance criteria. Then we convert or we can obtain the control transfer function from the state space model. Because all these designing procedure has been performed by the system on the state space model. So lastly, we have to convert from the transfer function from the state space model. So now we are coming on our case study, which is the designing a robust control, H-infinity robust control for a hydropower plant. Here you can say that it was a mathematical model of a hydropower plant. where you can see there is a controller. This is a normal controller. There is a governor system, there is a turbine system and power system, where G with suffix of small g is the transfer function of the governor system. G with suffix of T is the transfer function of the turbine system. G with suffix P is the transfer function of the power system, that is related to the generator. And here is the load, which may be vary. Y is the output, U is the reference signal or input. For this case study, we have taken some time constant which are as follows. You can see like governor time constant is 0.2 second, speed droop maybe 0.05. The main thing is the TW, that is the water starting time. There is an uncertainty due to this TW, and it so that it has been taken from 0.5 to 4 seconds. This depends upon the various parameters, so it may vary. And this is the various transfer function of that complete model. Here a result analysis. This is not the final result. Actually, this is the initial result, is initial simulation, where we can see that with the variation of the load, how much the frequency, that is the basic fundamental frequency of the power system may be vary. And you can say that is the 20%, 40%, 60%, 80%, there is a large variation in the frequency. And it may be that it is 2.5 to 3.5 hertz. So our major objective is to reduce this oscillation. This is the basic fundamental of the controller design. Here you can say W2 and W1 are the weight function. And for this controller design, we are taking the mix sensitivity method, which is also called as S over Ks problem. And the mix insensitivity involves finding a balance between achieving good performance in the closed loop system and maintaining robustness in the presence of uncertainties or disturbance. It has majorly two aspects. The first one is to minimize the sensitivity of the closed loop system to external disturbance. Second one is to involve minimizing the sensitivity of the closed loop system to change in the reference input. So here you can see that we have to minimize, the ultimate goal is to minimize the gain with W1 and W2, and that should be less than or equal to 1, not more than 1. Here is the procedure. Once again, I already discussed that what are the procedure, and through this procedure we have obtained the transfer function of the robust control. We have taken the transfer function of the governor, turbine and generator, and then through some MATLAB functionality we have taken the TW as as a best fit model, and then finally we got the transfer function of the robust controller is like this. You can see there is this is third order controller. And the same is going to be implemented in the simulation. Here you can see the simulation of the MATLAB through Simulink. There are two different ways for the simulation. First one is, the top one is without, without the controller, that is the robust controller. Second one is the bottom one is with the controller. And three block you are just here. You can see these are the blocks of the transfer function of the governor, then the transfer function of the turbine, and the transfer function of the generator. And there is a step input. So we have to see what are the effect due to this step input without controller and with controller, and how it reacts. So this is the final result. Here you can see there is the red one is the unit step reaction by the system, that is the plant. that is without K, and the black one is the with robust controller. And you can see that there is a large steady state error without the controller, and that steady state error is going to minimize with the controller. So from this result we can say that the responsiveness of the system is investigated without and with the H infinity control, and we have seen that there is a substantial steady state error which can be reduced with the help of H infinity controller, and system resilience is attained. So now come on our conclusion. In complete study, we have seen that there is a large oscillation in the power frequency with the changes of load, and H infinity based robust controller has been designed for a hydropower plant. The simulation results demonstrate that across a wide range of operations, the system ultra frequency oscillation may be successfully suppressed. And the main thing is further there is a large scope to investigate and more tuning of this controller for more better performance. So just I am concluding my presentation. Thank you.